A determinant is a single scalar number that tells us about the properties of a square matrix. This lesson will be about how to get a determinant from a matrix, starting with 2x2 matrices. For a matrix A of the form ABCD, the determinant is given by the formula AD minus BC. Also notice that there are different ways of denoting the determinant. We can call it det A with brackets, or what looks like the absolute value of A, but absolute value of a matrix doesn't really make sense. When we have bars like that around a matrix, it means the determinant of a matrix. Suppose we have the matrix A as 3, -1, 2, -5. The determinant is simply AD minus BC, 3 times -5 minus -1 times 2, -13. For determinants of larger dimensions, we have a method called cofactor expansion, and it's given by this awful looking formula. There is a scary sigma, it's a summation, we're going to add stuff. Then there's the entries themselves, the A, ij, and then there's a -1 and also an m. The m is called a minor, is the smaller determinant that we get from crossing out row I and column j of a matrix. Even though the formula looks a bit complicated, to actually do cofactor expansion, it's not that bad. Taking a look at this example, we are asked to find the determinant of this matrix. The first step is to choose a row or a column of the matrix to do cofactor expansion. A helpful hint to keep in mind is to pick the row or column with the most zeros. In this case, let's pick column 1. We could also pick row 1, it's the same. Row 1 and column 1 both have a single zero. Cofactor expansion along column 1 now. We account for the -1 in that cofactor expansion formula by drawing this grid pattern of alternating plus and minus signs. Remember that there is always a plus sign in the top left corner of the matrix. Applying these signs to our matrix, we have plus, minus, and plus. We take the 0 and cross out the row and the column that contains the 0, and then get the determinant of that. That determinant, the smaller determinant, is our minor. Then we add 3, but recall those signs, the plus and minus signs, so it's a -3, and then we cross off the row and column that has the 3 and get the determinant of that. And then 1, there is a plus sign, so we don't change the sign of that at all, it's just a +1. Cross off the row and column that contains the 1 and get the determinant of that. And we simplify our work. Now here's the reason why we want to pick the row or column with the most zeros to do cofactor expansion. Because 0 times whatever is just 0. That really simplifies these calculations. So the first chunk of this determinant equation is 0. Now -3 is multiplied by that determinant. It's a 2x2 determinant, AD minus BC. -3 times 1 minus -1 times -2. Then plus 1, and then again AD minus BC. -3 times -4 minus -1 times 2. The determinant of this entire matrix is 29. Here's a more difficult example. It's a 4x4 matrix for which we want to get the determinant. We follow similar steps as before. Look for a row or column that has the most zeros. Looks like column 3 has the most zeros. And then we assign plus or minus signs, keeping in mind that these signs alternate and the top left corner has to be a plus. Along the third column, we have plus, minus, plus, minus. Now we do cofactor expansion along this third column. 0 multiplied by the determinant that we get when we scratch off the row and column that contains the 0. 6. But remember, there's a negative associated with that 6, so it's a -6. Then cross off the row and column that has the 6 and get the determinant of that. And we have another 0. Cross off the row and column that has the 0, and then get the determinant of that. Then -5. But there is a negative associated with that -5, so it's a -5. Cross off the row and column that contains the -5, and then get the determinant of that. Here's why we want to pick the row or column with the most 0 entries to do cofactor expansion, because all those stuff with zeros just multiply to 0. We repeat the method of cofactor expansion for these minors, these smaller determinants. Looking for a column or a row with the most zeros, row 3 looks like a good choice. Cofactor expansion along row 3. We have -2, then cross off the row and column that has the -2, and then get the determinant of that. And we have a 0. There is a minus sign associated with that, but whether if it's a +0 or a -0, it doesn't matter because it's a 0. and then 1. Cross off the row and column that has the 1, and then get the determinant of that. Let's work on the other determinant now. Look for a row or column with the most zeros. Row 2 looks like a good choice. Column 3 is also good too. Cofactor expansion along row 2. We have -1, but then there's a negative sign associated with that -1, so it's a -1. Cross off the row and column that has the -1, and then get the determinant of that. Plus -2, cross off the row and column that has the -2, get the determinant of that. And we have a 0. It's a -0, but it doesn't really matter because it's a 0. Now we compute these 2 by 2 determinants, remember AD minus BC. It's really important to use brackets here to organize what's multiplying with what. -6 and then big brackets, -2 is multiplied by AD minus BC, 1 times -1 minus 1 times 5, plus 1 times AD minus BC, 3 times 5 minus 1 times 1. We now close the big brackets on the -6, and we work on the other determinant that's multiplied by 5. In brackets, we have 1 multiplied by AD minus BC, 1 times -1 minus 1 times 5, and then minus 2 times AD minus BC, 3 times -1 minus 1 times 1. Simplifying everything, we have the determinant as -146. There are some shortcuts that we can take for calculating determinants. If we have a matrix that is triangular or diagonal, then to get the determinant, we just multiply all the entries along the main diagonal. If the matrix has a column or row that's all zeros, then the determinant is automatically 0. Here we have a lower triangular matrix. The determinant that we expect would be the product of all the entries along the main diagonal, 1 times 3 times 5. We can do cofactor expansion to see if that's actually the case. Do it the long way. Det cofactor expansion along the first row, we have 1 multiplied by the determinant that we get when we scratch off the row and column that contains the 1, and then 0, but there's an associated minus sign with it. Get the determinant of that. That entire term is going to be 0, and then plus a 0 multiply by the minor, but then that's also going to be 0. And then we do AD minus BC on that 2 by 2 minor. 3 times 5 minus 0 times 4. So yes, in fact, we do have 1 times 3 times 5, 15 as det. In part B of this example, matrix B has a column of zeros. The determinant of B is 0. Here are some properties of determinants that we have to memorize. Adding or subtracting a multiple of one row to another actually doesn't affect the determinant. We can use that to our advantage. We can simplify the matrix, get as many zeros as possible before doing cofactor expansion. Each time we flip a pair of rows, we're going to multiply the determinant by -1. If we were to swap an even number of rows, we actually don't do anything to the determinant. Let's say we flip 2 pairs of rows, then we get a -1 in the determinant. Then we flip 2 pairs of rows again, any 2 pairs. Then we multiply the determinant again by -1, so that -1 in the first instance gets cancelled by the -1 in the second instance. Transposing a matrix does not affect the determinant. If we multiply a row by a scalar constant like k, then we're going to multiply the determinant by k. If we multiply 2 rows, then we're going to multiply the determinant by k twice, and so on. Which means, if we multiply the entire matrix by k, we're going to multiply the determinant by k to the n times, n being the dimension of that square matrix. So let's say if the matrix is 4 by 4, and we multiply k to that 4 by 4 matrix, the determinant is going to be k to the 4 det. Interestingly enough, when we have 2 matrices multiplied together, the determinant of that product is equal to the product of the determinants. Det is equal to det multiplied by det. And similarly, if we were to raise a matrix to a power, let's say k, then the determinant is also going to be raised to the power of k. It's equivalent to multiplying that many det together. When we invert a matrix, we reciprocate the determinant. Although keep in mind, if we have 2 matrices added together, the determinant of a sum of matrices is not necessarily equal to the sum of the determinants, meaning that if we have the determinant of a plus b, it's not necessarily the same as determinant of a plus determinant of b. Given that the determinant of this matrix is equal to 7, we have to use the properties of determinants to get the determinant of this matrix. We're going to work backwards. We're going to simplify this matrix into the matrix for which we know the determinant. Let's flip rows 1 and 2. We're going to introduce a factor of -1 to the determinant. See those 3x, 3y, and 3z? Let's factor out a 3 to get x, y, z. In row 2, we have u plus x, v plus y, w plus z. Let's go row 2 minus row 3 to get rid of those plus x plus y plus z. And remember, adding and subtracting multiples of one row to another does not affect the determinant. And now we have this determinant for which we know is equal to 7. Multiplied by all those changes that we did, the -1 and the 3, our answer is -21. We're going to practice some more using the properties of determinants to calculate determinants. We're told that det A is -1, det B is 2, and det C is equal to 3. We have to evaluate all these determinants, and we're told that all these matrices are 4 by 4. The determinant of 2 times A transpose B to -2. We kind of see two matrices multiply together here, the stuff with A and stuff with B. So then the determinant is going to be determinant of stuff with A multiplied determinant of stuff with B. We can break down that det 2A further. Since A and all these matrices are 4 by 4, multiplying A by 2 introduces a factor of 2 to the 4 to the determinant. And now with B, when we invert a matrix, we reciprocate the determinant, so put that determinant in the denominator. And then that power of 2, we're going to exponentiate that determinant. We can put some numbers in, 2 to the 4, and then det A transpose, transposition doesn't change the determinant, so it's just det A, -1. And then 1 over det B squared, det B is 2, so 2 squared. And simplifying, we have -4. Find a determinant of -A times B to the 3. When we have two matrices multiply together, we also multiply the determinants. We get det -A multiplied by det B to the 3. That negative, think of it as a factor of -1. We can factor that out. A is 4 by 4, so det A is multiplied by -1 raised to the power of 4. Determinant of B cubed, that's equal to determinant of B cubed. Putting our numbers in, we have -8. The determinant of A times B times C, the whole thing inverse. Inverting a matrix reciprocates the determinant, so it becomes 1 over det of ABC. The determinant of A times B times C together is equal to the product of these determinants, det A times det B times det C. Putting in the numbers, we have 1 over -6.